Okay, in this video, I would like to explain to you the constant of time, also known as tau, and I also want to show you a couple of ways to calculate tau for patients on mechanical ventilation. So before talking about tau, I would like to touch upon the concept of exponential decay. So in general, a quantity is subject to exponential decay if it decreases at a rate proportional to its current value. This can be described by a first order differential equation as follows. And so for this example, we're talking about a quantity being the volume. So the change of volume over time is proportional to the volume itself. And so in a way, this is similar to how you think of a half-life in radioactive decay. This graph is taken from the article on Wikipedia, and you see different exponential decay curves. And all of these curves, the decay of that quantity is proportional to the quantity itself. However, what's different is the rate by which the quantity decays. And that's something that the constant of time, tau, plays into. So the time constant tau represents the time that's needed for the volume in the lungs to decrease or to decay by a value proportional to that volume. It can be measured during inspiration and expiration. However, the time constant during expiration is clinically relevant in diagnosing and troubleshooting air trapping or autopsy. And the time constant, or tau, is expressed in seconds. This is a nice graph taken from the website derivation.com. This graph illustrates or shows you the volume over time measured in multiples of tau. So starting at time 0, the patient has 100% of the initial volume, so that's the initial volume itself. After 1 tau, that volume is down to 37%. After 2 taus, the volume is down to 13.5%. And then after 3 taus, the volume is down to 5%. So there's only 5% of the initial volume remaining. This table shows you the same numbers. And so after 1 tau, the volume is down by 63%, and the 37% remaining. After 2 times tau, the patient would have exhaled 86% of the initial volume and would have 14% of volume remaining in his lungs. And then finally, after 3 taus, the patient would have exhaled 95% of the initial volume and would only have 5% of volume remaining. And so we think of 3 taus as being the minimum of the tau that we aim for in order to avoid air trapping. Note that if tau is less than 3, you end up with significant volume remaining in the lungs, and hence propensity for air trapping or autopsy. So some clinical correlations with the tau. So a short time constant signifies a decrease in compliance. This is something that you see in ARDS. Can also be due to a decrease in resistance. So for instance, a patient who initially presented with asthma and now is recovering. A long time constant can be seen in increased resistance. So an asthma exacerbation, for example, and increased compliance. This is your patient with COPD. Note though that you can have a mixed condition where you have a decrease in compliance and an increase of resistance, which can result in a pseudonormal time constant. Think of your patient who has COPD and now is presenting with acute respiratory distress syndrome, for example. Okay, let me now summarize the discussion by using equations. So we started with this initial equation that reads as dV over dt, or the rate of change in volume equals the volume itself divided by tau. So that means that the rate of change in volume is proportional to the volume itself and is inversely proportional to tau. This is a first order differential equation, and the solution to this differential equation is this equation here. So the volume at the time of tau equals the initial volume V0 multiplied by e to the power of minus t over tau. It's a complicated equation, but the way to think of this equation is a way to get the table below that we clinically use when calculating tau. And so let's take the first row in for example, where t equals 1 tau. And so if you put 1 tau here in this equation, then that equation reduces to v equals v0 multiplied by e to the power of minus 1. E is the natural number, which is 2.72. And e to the power of minus 1 is the inverse of e, which is 0.37. And that's where that 37% remaining comes from. So again, think of this initial equation as a way to derive this table, which we will use when calculating tau. The second way to think of the equation is as follows. So dV over dt is the change of volume over time, and that basically is flow. And so this can be written as flow equals minus volume divided by tau. And if you rearrange this equation, you can actually calculate tau being minus volume divided by flow. And this would be a second way to clinically calculate tau, which we will see when we use the simulator. The last equation is tau equals resistance times compliance, and I won't go into the derivation of this equation, but this equation helps you to think of clinical correlates with the time constant. And so, for example, think of asthma as a condition where you have an increased resistance and hence your tau will be increased. Think of your COPD as a condition where your compliance is increased and hence your tau will be increased. And finally, think of your ARDS as a condition where your compliance is decreased and hence your tau will be decreased. So how to use the time constant in mechanical ventilation? Well, you can use it to assess respiratory mechanics and changes in them. Second, you can calculate tau as long as you have a patient who is passively exhaling. And you can also use it during non-invasive mechanical ventilation as long as there's no leak. In general, you want at least 3 times tau to avoid auto-peeping or air trapping. And so let's take a look at this ventilator waveforms, for example, and I want you to focus on the second waveform, which is the flow. So let's take a normal patient. That patient has a tau of 0.7 seconds. Note here that the flow has 2 phases. So you've got an inspiratory phase where you have a positive flow, so that's air going into the patient, and then you have an expiratory phase where the patient is exhaling, so air is going out of the patient, and hence you have a negative flow. So you start at your peak flow, and then the flow is gradually going to taper down before the next cycle. So if we think of this patient with a tau of 0.2, then we can say that we at least need 0.7 times 3. So that's about 2 seconds for the patient to exhale before the next cycle. And if you see here, we started at second 1. So I'm going to need roughly about 2 seconds. So that's the first second, and that's the second second. And indeed, this patient is almost finished with exhaling before the next cycle is out. So that patient is at low risk of auto-peeping or air trapping. This is a patient who has COPD. So COPD, think of COPD as increased compliance, increased time constant. And so the tau in this instance is 2 seconds. And so this patient needs 2 times 3, at least 6 seconds before for exhalation in order to avoid air trapping. This is obviously not the case here. If we count the time for exhalation, we've got 1 second, 2 seconds, 3, 4, 5. So we only have 5 seconds for exhalation. And you can clearly see that there is still flow from the patient before the next cycle is delivered. So this patient will have a degree of autopsy. Let's take ARDS. So ARDS is a clinical situation where you have stiff lungs, and so low compliance. Low compliance translates into low time constant. So the time constant in this example is 0.5 seconds. 3 times that is roughly about 1.5 seconds. So this patient has plenty of time to exhale before the next cycle is up. And indeed, in ARDS, auto PEEP is not something that we typically see given the stiff lungs and the low compliance. And so you can clearly see that the flow was back to 0 before the next cycle is delivered. Okay, now I want to show you how to clinically calculate your tau for a patient who is on mechanical ventilation. Note that almost all modern mechanical ventilators would have mechanism to calculate the tau and to provide it to you. However, knowing the physiological basics is very helpful when assessing patients. So I'm going to the website iclearning.com, and then I'm going to go to a normal lung scenario. And so what you see here is the mechanical ventilation waveforms. And we are going to calculate the tau using 2 methods. The first method is going to be using the tables that are provided in the previous presentation. So I will pause the simulation, and then I'm going to go ahead and pick the first waveform. And I will move my slider until I get to the tidal volume, the delivered tidal volume, which is in this instance 500. And so note that the patient started exhalation with 500 milliliter of volume, and that happened at time of 0.48 seconds. And so let me write those numbers down. So this is my cheat sheet. I will write time 1 equals 0.48. And then my initial volume was 500 milliliter. And so if I am doing 1 tau, that means that the patient would have 37% remaining after 1 tau of time. And so 500 times 0.37 equals 185 milliliter. And so I go back to my simulation screen. Again, we started at 500 milliliter of volume at 0.48 second, and then I move the slider down until the patient is down to 185. So 186 is good enough. And then I note the time here is 1.46 seconds. So I'm going to write T2 equals 1.46 seconds. And the difference between those 2 times is 1 tau, or is the time constant. And so T2 minus T1 equals 0.98 seconds. So tau is roughly 1 second in this case. So that's the first way to calculate tau. Let me clear the screen, and then I'll show you the second way. So the second way, you also focus on the expiratory phase, since we're calculating the expiratory tau. And then you select any point in expiration, preferably early during expiration. And you take a note of your flow and volume. And so for this instance, for instance, at this point in time, at 0.82 seconds, the patient had a flow of minus 21.7 and a volume of 355. So I will go ahead and write those numbers. So I will write flow equals minus 21.71, and volume equals 355. Note though that you have to have the units matched up. And since my flow is in liters, I will convert my volume to liters as well. So that's 0.355 liters. And also note from the prior presentation that tau equals minus volume divided by flow. And so if you do that, you get your tau, which is 0.016. And you may say, well, my tau is almost, 1 second in the previous calculation. Note in this calculation that the ventilator is reporting the flow in minutes. And so you have to convert, your tau to seconds. So in other words, the 0.016, the unit here is minute. And so in order to convert that to second, I have to multiply by 60. And I basically get the same number, which is 0.98. So in both of those instances, I got a tau that's roughly equivalent to 1 second. One last note, since this is a simulated case, you can calculate the tau by knowing the patient's compliance and the patient's resistance. And we know that tau equals compliance times resistance. So in this case, it's 0.1 multiplied by 10, which is 1 second. And so in all of the 3 cases, we got the same calculation. Tau in this case equals 1 second. That's all for this presentation. Thank you.